I'm Dr. Sreedevi, Assistant Professor, IARE, Hyderabad. Today in this session, we are going to Graph Theory Review of Basics 4. In this session of lecture, I'll be dealing with some enumeration on trees, Cayley's theorem, 2 seconds, and matrix tree theorem. This matrix tree theorem and 2 seconds are associated with Cayley's theorem, and we'll see some examples. Tree enumeration. The subject of a tree enumeration is concerned with the problem of finding how many non-isomorphic graphs possess a certain property. We all have seen what is isomorphic graphs, and these isomorphic graphs possess certain properties. I just want to recollect what is isomorphism of graph. Two graphs G1 and G2 are said to be isomorphic if we can find an one-to-one relation between the vertices of G1 and G2 and the edges of G1 and G2, and there should be an incidence relation between the edges and vertices should be preserved in both G1 and G2. That is, we have to find a one-one relation between both G1 and G2, then with the graph G1 and G2 are said to be isomorphic. Here we are saying how many graphs possesses, how many non-isomorphic graphs possess given property. Actually, the subject was initiated in 1850s by Arthur Cayley. Most of you might have heard the name Arthur Cayley related to this periodic tables of chemicals and all. In the process of when he was finding in the problem, the subject was initiated in 1850s by Arthur Cayley, while he was in the process of finding structural isomers of saturated hydrocarbons CkH2k plus 2. Okay, we'll see how this enumeration was done. Cayley represents CkH2k by a connected graph with carbon atoms representing vertex with degree 4 and hydrogen atom with degree 1. Why this carbon atom? We all know that carbon atom has the valency of 4 and hydrogen has the valency of 1. That is why Cayley represented CkH2k by a connected graph with carbon atom having vertex degree 4 and this hydrogen atom with degree 1. So how will the condition when this k equal to 1, that is C, instead of writing C1, we will be writing as CH4, right? How it will be? Then according to the Cayley construction, it can be represented by C with 4, the carbon atom. If it is that it is represented by C like this, it has 4 valencies. And it has 4 hydrogen. And the degree of each hydrogen, here coming the vertex with hydrogen, the degree is 1 and the carbon with 4. What happens if it is C2, then C2H, 2k plus 2 means 2 into 4 plus 2, 6, right? C2H6. How to represent that? 2 carbon atoms are represented like this. And 6 hydrogen atoms coming here. Hydrogen, here hydrogen, here also another hydrogen. 6 hydrogen. I hope now you might have got some idea regarding this trees and some graph and all, how it is going to be, right? Yeah, this represents a tree. How it comes? Let's see. Total number of vertices n in such graph is n equal to k plus 2k plus 2. Why? Because we have CkH2k plus 2, right? So the total number of vertices will be k plus 2k plus 2. Which will be 3k plus, on simplifying, k plus 2k, 3k and plus 3k plus 2. And total number of edges we have to find. We know that sum of degrees in a graph is equal to twice the number of edges. From that we are writing here E equal to half the sum of degrees. Because here we are not familiar with, we have drawn a graph here there, but we are not sure about the number of edges. So here we are using this formula, half the sum of degrees. It is equal to half, and this carbon atom constitute degree, each carbon atom constitute degree 4. So it is 4k, and each hydrogen atom constitute degree 1. That is 2k plus 2. Okay. This on simplifying, we get 4k plus 2. And half of that is 3k plus 1. And now look at this equations 1 and 2. We have n equal to 3k plus 2 and e equal to 3k plus 1. Okay, here 3k plus 2, here 3k plus 1. What is that? Yeah, getting some idea with the trees and all. Yeah, when we are connected graph is said to be a tree if it has n edges and n minus 1. A connected graph is said to be a tree with n vertices and n minus 1 edges. Here it has 3k plus 2 vertices and 3k plus 1 edges. That is 1 less than the number of vertices. Then number of edges is 1 less than the number of vertices. Thus we get a graph which is connected and number of edges is 1 less than the number of vertices, which implies that G is a tree. Either we have tried this CK H2K plus 2 and we got a tree structure itself, right? Yeah, here it is getting that it is a tree. There's a real life problem of counting the structural isomers of given hydrocarbons became the problem of counting trees. That is, when Cayley was studying the properties of structural isomers of hydrocarbons, he encountered with the problem of counting the non-isomorphic trees. Cayley proposed this problem. What is the number of different trees that one can construct with n distinct vertices? And also, it has to be labeled trees, specifically labeled trees. Why? Because we are using two different labels, they are hydrogen and carbon. Okay, there we are using that like that. And when it is coming to there, we were using two different labels. And now what we are going to do that? Okay. So what is the number of different label trees that one can construct with n distinct vertices? And we will see how to do it. Now consider this figure of representing 3 ways of labeling a tree with 4 vertices. Here consider this. For the sake of simplicity, I have drawn like this only. Let it be a path with 4 vertices, and the 4 vertices are marked A, B, C, D. Next, I have marked as D, C, B, A. Do you find any kind of difference between these first two? It is just 2 is just writing the reverse order. So it is 1 and the same. Whereas A, B, D, C, this third figure is entirely different from the first figure and the second figure. Actually, when we are given 4 points, we will be getting 4 factorial different ways of representing. And of this, considering the same things, discarding the same things, and we will be getting 4 factorial by 2, that is equal to 12 ways of representing these trees. Okay? When we are given 4 points, and we will be getting 4 factorial by 2 different ways of representing a figure like this. When we are considering, if you are considering like this is also a tree with 4 vertices, right? How many ways this can be represented? Because this central vertex can be named either as A, then we can B, C, D here. If I am writing name, it is B, A, C, D. Same way, C, A, B, D. If it is D, A, B, C. Thus we will get 4 different ways of representing a figure like with 4 vertices. Okay, like this. So in total we will get 16 different ways of representing a tree with 4 vertices. Earlier we have seen if we are representing like this, we can have 12 different ways, and if we are representing like this, we will have 4 different ways. That is, with a tree with 4 tree with 4 labeled vertices can be represented in 16 ways. Okay, now we will see this representation, how it will looks like. Now I have represented these vertices like A, B, C, D. And we know when there are 4 vertices, a tree will consist of 3 edges. And these are the 16 different ways of representing, connecting A, B, BC and DC. The same thing. Okay, these all are 1, 2, 3, 4. 1, 2, 3, 4. Thus, we got all the 16 representation. Look, what is the difference between labeled graphs and unlabeled graphs? Labeling increases the number of representations. If it was all unlabeled graphs, we will be getting only one representation for all these things, right? I hope you remember what is the difference between labeled and unlabeled graphs that we have already discussed in our lecture series. And the Cayley's theorem is the number of labeled trees with n vertices where n greater than or equal to 2 is n power n minus 2. Here, is it true with this case of, is it n power n minus 2? When n equal to 4, what will be? 4 power 4 minus 2, which is equal to 4 power 2, which is equal to 16. Here we have got it, right? So what will be happening? How many different labeled trees you will find when n equal to 5? We will be getting it as n equal to 5. When n equal to 5, it is 5 power 5 minus 2, which is equal to 5 power 3, which is equal to 125. Okay. Draw all labeled trees with 3 vertices. While doing these labeled trees with 3 vertices, we can name it as A, B, C. Okay. I have put A, B, C. How many trees then we can expect here? We can 3 power 3 minus 2, which is equal to 3. Okay. So I am just marking first figure, second figure A, B, C, and 4 here also A, B, C. First I am connecting AB. First I am connecting this AB and BC. Then connecting AB and AC. Then connecting AC and CB. Can I draw any other graphs than this? No. I can draw graphs, but it won't be trees. Okay. These are the only 3 labeled trees with 3 vertices. So, Cayley's theorem states that a number of labeled trees with n vertices where n greater than or equal to 2 is n power n minus 2. Now we are going to prefer sequence. In combinatorial mathematics, prefer sequence of a labeled tree is a unique sequence associated with a tree. The sequence for a tree on n vertices has length n minus 2 and can be generated by a simple iterative algorithm. The prefer sequence was first used by Hans Prefer to prove Cayley's formula in 1918. That is nearly after 68 years when Cayley has proposed this theorem. The prefer sequence was founded. We will see how this sequence works. Algorithm to convert a tree into a prefer sequence. First, the labeled prefer sequence is generated iteratively by removing the vertices of a tree until 2 vertices remain. Consider a labeled tree with vertices 1, 2, 3, etc. n. At step I, remove the leaf with smallest label. I hope what is this leaf? Vertex with degree 1 is termed to be a leaf or pendant vertex or in a tree. This leaf with the smallest, first at the step I, remove the leaf with smallest label and set the ith element of the prefer sequence to be the label of this least neighbor. That is, you have to put the ith element of this sequence to be the neighbor of the leaf which we are removing, we have to put the label of that label of the neighbor of that leaf. The preferred sequence of a labeled tree is unique and has of length n minus 2. If we are given a tree with n vertices, we will get an unique sequence of length n minus 2. This preferred sequence of a given tree will be always unique. Okay? Because while considering this minimal trees and all, while considering the spanning subtrees, will it be unique always? No. But while considering this preferred sequence of a given tree, it will be unique. Now consider this tree with vertices are named 1, 2, 3, 4, 5, 6. Okay. First, this preferred sequence first process is vertex 1. Here vertex 1 is the vertex with smallest label. So we are removing this vertex with vertex 1, label 1. So we are adding, what is the neighbor of this vertex with vertex named with 1? Its neighbor is 4. So we are adding 4 to the first number. 4 as the first number on the sequence. Then the lowest leaf which is labeled, it is vertex 2. This is 2. So when we are removing this 2, what is the neighbor of this 2? It is again 4. And then comes 3. Okay. Then again 4. So all these things are removed. So what will be this? It will be a tree with 4, 5, 6. Now which vertex which we can remove? This 4. So when we are considering this, removing this 4, it comes as 5. Now, so what is that? Written in this slide. If vertex 1 is here, the vertex 1 is a leaf with smallest label. So it is removed first and its neighbor 4 is put in the sequence. Then the vertices 2 and 3 are removed simultaneously. So again 4 is added twice. Now 4 is a leaf with the smallest label. Because 4 is a leaf and 6 is also a leaf. But here the leaf with smallest label is 4. So we are removing 4. And so the now 5 is the neighbor of this vertex 4. Vertex labeled with 4. Now we are adding 5 to this. And now we can stop the process as we are left only with 2 vertices here in the given graph. The sequence is formed is 4, 4, 4 and 5. Okay. This is the preferred sequence of a given tree. So it is an iterative process because we are starting from one point and we are just simply adding, moving to next steps. The immediate consequence of preferred sequence is that the sequence provides a bijection between the set of labeled trees on n vertices and the set of sequences of length n minus 2 on the labels from 1 to n. The second set, we know that there are n raised to n minus 2 size. The second set, we know that it is of size n raised to n minus 2. So the existence of bijection proves Cayley's formula. That is, there are n raised to n minus 2 labeled trees on n vertices. Okay, this Cayley's formula is proved with this preferred sequence. Okay. Next, now we move to once again we are going to construct a chord and then we will see how to construct a tree if a chord is given. Now consider this tree. Here which leaf is of the least labeled vertex? This is 2. So we are removing 2 and so we are adding 6 to our sequence. Then which one is the least weight? Here this 3 is there. So we will remove 3. And which is the neighbor of 3? It is 5. So we add 5 to that. Then again, what is that condition? Then 4 is the least one. Then we will be removing this 4 and we'll be adding 6. And now we will be getting this 6, 5, 1, 7. And now which is the leaf with least weight? Though 1 is here, is it a leaf? No, because it is not a leaf. Here we have 6 as the least with least weight, because here we'll be having 6 and 7. Of this, 6 is the least weight. So remove 6 and we again put 5. Now out of this we will be getting 5 is the with least weight, labeled, and so we'll be removing 5 and we can put 1. So the required proof of sequence is 6, 5, 6, 5, 1. Okay. Now I hope this getting a proof of sequence from a given tree is now okay. Now we'll see how to convert a proof of sequence to a tree. Let A1, A2, etc. A and be a proof of sequence. We have already seen that when a tree is given with n vertices, the proof of sequence will be containing n minus 2. The sequence will contain n minus 2 points. Suppose if we are given this sequence A1, A2, etc. A, then the given tree will have n plus 2 nodes, numbered from 1 to n plus 2. For each node in the set, its degree in the degree is the number of times it appears in the sequence plus 1. That is also here. Here this 6 appears twice. So this when we are considering this a tree with vertex name 6, it will be 1 plus the number of times it is appearing in this. Here it is 3, right? Here also the 5 is appearing twice, so here the degree of related to this vertex with the label 5 is 3. Okay, here also it is the same, right? A1, A2, etc. A and B a proof of sequence. Then the tree will have n plus 2 nodes numbered from 1 to n plus 2. For each node in the set, its degree is the number of times it appears on the sequence plus 1. Next, for each number in the sequence AI, find the lowest number not Aj with degree. Sorry, not J with degree equal to 1. At the edge Aij to the tree and decrement the degrees of J and Aj. At the end of this loop, two nodes with degree 1 will remain. Call them U and V. Add an edge UV to the tree and we will get the final tree. It looks some like, but we will see how it is. Now we will be starting with the given sequence of the earlier tree that we have considered. It is 6, 5, 6, 5, 1. Comparing it with the general sequence A1, A2, etc. An. Let B1 be the smallest number not appearing in the sequence. When we are considering from here we have 5 nodes, right? So the tree will be considering the nodes to 7. And that will be numbered from 1, 2, 3, etc. 7. That is the rule that we have been following in considering the proof of sequence of a tree. And this, when considering when B1 be the smallest number not appearing in the sequence. So what will be the what number we can take it as B1? Here, the smallest number not appearing in the given sequence is 2. Okay. And then add join B1 and A1 and remove A1 and B1 from consideration and proceed successively like that. Find B2, then add B2 and A2, then etc. We can find that things. Thus we will be getting B1 equal to 2, B2 equal to 3, B3 equal to 4, then B4 equal to 6. Why? Here this 6 has appeared twice. And one more thing will be happening this with this 6 and B5 equal to 5. And the corresponding edges that we form are this, because 6, this with this 6 and 2, 5 and 3, then this 6 and 4, then this 5 and 6, then this 1 and 5. Okay, join these edges. And last 2 vertices that we are left with is 1 and 7. We have not considered this 1 and 7. Because we have to number up to 7. Because you may be thinking from where this 7 came. Yeah, because this sequence has 5 digits. And so the tree should have 7 nodes. And this 7 and this 1 which has been dealt only once. And we will be connecting this 1 to that 7. and we will get back the tree back like this. That is, first we have 6 2 5 3. That is 6 2 5 3. Then which are 6 4 5 6. Then we are putting this 6 4. 5 6 is being added here. Then we have 5 1 here, and then 1 is added to 7. That is how we can find a prefer sequence from a given tree, and we can draw a tree from a given prefer sequence. Okay, that is, this prefer sequence is giving how many distinct labeled trees can be found when number of n vertices. How many distinct labeled trees can be found with n vertices? That is, we can find a bijection here, and it is given bijection from n to this n minus 2 sequence. That is the prefer sequence. Here we are finding a bijection from the n vertices to the sequence of length n minus 2, and this sequence of n minus 2 has size this n power n minus 2. Okay, then we can find that is there are n power n minus 2 labeled trees on n vertices. Now we are going to see what is this matrix tree is. Actually, matrix tree, the term matrix tree is referred by Kerau's theorem. Matrix tree theorem is also referred as Kerau's theorem or Kerau's matrix tree theorem, named after Gustav Kerau, which gives a number of spanning trees in a graph. He was related as an electrical engineer, and in this electrical networking, he found this thing. Shown that the number can be computed as using the Laplacian matrix of a given graph. It is a generalization of Cayley's formula, which provides a number of spanning trees in a complete graph. To see what is this matrix tree theorem, we will first see what is this Laplacian matrix. Okay. Laplacian matrix of some symbol graph is defined to be graph with n vertices is defined as Ln by n. That is a n by n matrix, that is a square matrix. It is defined as L equal to d minus a. What is this d? I hope you remember what is this adjacent a. It is the adjacency matrix. And what is this d? It is the degree matrix of a given graph. And a is the adjacency matrix. And since G's given graph, G is symbol graph, this a consists of ones and zeros, and the diagonal elements are all zeros. In the case of directed graphs, the degree, when we are considering the degrees, there are two kinds of degree. I hope you remember it. It is just in degree and out degree. And we will be considering either in degree or out degree for the cases of, in the case of directed graphs, depending on the application. Okay. Now we will see the elements of what the elements of n by n will be. It will be degree of Vij if I equal to j, equal to minus 1 if I not equal to j and Vi and Vj are adjacent, equal to 0 otherwise. Now we will see, consider this graph with vertices are named 1, 2, 3, 4, 5, 6. So the Laplacian matrix will automatically a 6 by 6 matrix. Okay, and we found that it is equal to degree of Vi if I equal to j. Here V11 means it will be 2 as degree of 1. Okay, then 1 is adjacent to 2. So it is placed by minus 1. 1 is adjacent to vertex named with 5. So it is here also minus 1. Other things, if they are not adjacent to any points, then it will be zeros. It is equal to degree of Vij. Sorry, it is equal to degree of Vi if I equal to j equal to minus 1 if I not equal to j and Vi is adjacent to Vj. Equal to 0 otherwise. So we write the Laplacian matrix like this. Okay, when considering this fifth row, that is we are considering with vertex with the label of vertex, fifth vertex. If it is the fifth vertex, it is adjacent with vertex named 1, first one, minus 1. then it is adjacent with vertex 9 with 2, so minus 1 here. It is not adjacent with it is third vertex, so it is 0 here, and it is adjacent with this vertex 4, so it is minus 1 here. And what is vi? When I equal to j, it should be the degree of that vertex. It is here 1, 2, 3 here. Is it adjacent with this vertex 1, 6? No, so it is 0. So it goes the Laplacian matrix of this graph G. If it is the G, this is the L of G. Okay. For a given connected graph G with m n labeled vertices, like lambda 1, lambda 2, etc., lambda n minus 1 be the non-zero eigenvalues of its Laplacian matrix. The number of spanning trees of G is given by T of G equal to 1 by n into lambda 1 into lambda 2 into etc. into lambda n minus 1. I hope you remember what is this non-zero eigenvalue of a matrix. I'm not going deep into that. We can find this characteristic equation. Then for solving this characteristic equation, we will be getting these eigenvalues. If lambda 1, lambda 2, etc., lambda n minus 1 are the non-zero eigenvalues, then the Laplacian of the Laplacian matrix, then the number of spanning trees of a graph G is 1 by n into lambda 1 into lambda 2 into lambda 3 into etc. into lambda n minus 1. This is what Kerr's matrix theorem states. This theorem has another statement also. Let G be a simple graph with n vertices. That is, say the vertices of G be named as v1, v2, etc., vn. Let M equal to Mij be the n by n matrix, in which Mii equal to degree of Vi. Mij equal to minus 1 if Vi and Vj are adjacent. Mij equal to 0 otherwise. It is same thing as that we defined as for Lnn. Okay, it is the degree. Here we are writing as Mij II equal to degree of Vi. Here like that only, it equal to minus 1 if they are adjacent and 0 otherwise. The same thing here also. Then the number of spanning trees of G is equal to the cofactor of any element of M. What is this cofactor of any element of M? Yeah, it is the matrix obtained by deleting the corresponding row and column where the element occurs. Okay, it is the determinant of that element obtained by deleting the row and corresponding row and column where that element occurs. Then the number of spanning trees of G is equal to the cofactor of any element of M. How this M was defined as M equal to Mij, where Mij equal to degree of Vi, Mii equal to degree of Vi, Mij equal to minus 1 if Vi and Vj are adjacent, Mij equal to 0 if Vi and Vj are non-adjacent. Okay, so we have considered what is tree enumeration. That is, how many trees possess the same properties even though the trees are non-isomorphic. And then we saw that Cayley's theorem. If G is a given graph of n vertices, then the number of distinct labeled trees of that graph consists of n raised to n minus 2. And what is this preferred sequence? Preferred sequence gives a bijection with the n vertices and n minus 2 subsets of this. And we will see that which supports the Cayley's theorem and Cayley's condition. And what is a Laplacian matrix of a given graph? It can be defined as L equal to D minus A, and also L and N can be defined like that, as what we have seen here. It can be defined like this. If you need not memorize this thing, you can keep in mind this L equal to D minus A, where D is the degree matrix and A is the adjacency matrix. Okay, and this matrix tree theorem. I hope you enjoy this session. Thank you for watching. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.